So before we begin, if you like videos that explain math concepts simple, fast, and offer numerical examples, please feel free to subscribe, comment, and like. Now, let's begin with determinants. So let's say we're given this matrix right here. And in my last videos, we went over cofactors, minors, and row expansion. But what if you couldn't be bothered to do any of them? What if there was a third way to solve for the determinant of a 3x3 matrix? And it turns out this method is a lot more visual. And what I mean by that is we can grab this matrix, remove the matrix notation, copy and paste the first two columns and add them as additional columns. Here's what that looks like. Now, what's next is very similar to finding the determinant of a 2x2 matrix. What does that look like exactly? If you forgot how to do a 2x2 or find the determinant of a 2x2 matrix, well, it's going to look like this. And let's see here. So the arrow is pointing down. You're going to multiply the diagonals together, and you're going to subtract those terms by the arrows pointing up. So our first diagonal is 0 times -1 times 1, which is going to be 0. Our second diagonal is 2 times 2 times 4, which is going to be 16. And our third diagonal is going to be 1 times 3 times -4, which is -12. Now, go ahead and pause the video and do the same for the green arrows. Figure out the products of three diagonals. So if you did the actual math, this is what the products of the three diagonals pointing up should look like. And from here on out, we can solve for the determinant. And the determinant is mainly the sum of terms. Always remember, arrows pointing down, you add the products, and arrows pointing up, you subtract the products. Here's what that looks like. So you'll notice we're adding 0, 16, -12, and we're subtracting -4, 0, -6. And what does the determinant of the given matrix end up being? Turns out it is only +2. Now the process of copying and pasting the second columns and moving them as additional columns works for all square matrices of varying orders. I take that back. That is not true. It turns out the diagonal process that we have just done is only valid for matrices of the third order. My bad, guys.